Now that we know the derivative of cosine of x, so remember if f of x is equal to cosine of x, we just derived that the derivative of this was equal to negative sine x. And we saw that if our function g of x was equal to sine of x, the derivative of sine of x, that was equal to positive cosine of x. So we can use these rules now to derive all the other trigonometric functions by just using the quotient rule, because all the other trigonometric functions are in terms of sine and cosine. So if I look at, for instance, tangent of x, I know tangent of x is the same thing as sine of x over cosine of x. So if I want to find the derivative, so d dx of tangent of x, I need to use that quotient rule. So let's just write out the quotient rule again. So the quotient rule says we're going to look at the derivative of the numerator, so d dx of sine x times the denominator, cosine of x, minus the numerator, sine x, times the derivative of the denominator, so times d dx of cosine of x, all over this denominator squared. So cosine of x quantity squared. So now that we have what these derivative is, sine of x, the derivative of sine of x, it's the same sign, it's positive. So sine of x, this one is going to be cosine of x. Derivative of sine x is positive cosine of x. Then we have times this cosine of x right here, minus our sine of x. But now when we take the derivative of cosine of x, that was negative sine of x. So times negative sine of x all over cosine x quantity squared could be written a little differently. A lot of times we'll see it as cosine squared x. Well, cosine x times cosine x, that's just equal to cosine squared x. Minus, well, negative sine x times a negative sine x, so it really is plus cosine squared x. Sorry, sine squared x, looking at the denominator. Sine squared x, all over our denominator, cosine squared x. We're almost there. Cosine squared x plus sine squared x, that one really should look familiar to you. That's our trig identity, Pythagorean trig identity, and that's 1. So we have 1 all over cosine squared x. If we really want to think about it, let's rewrite that in terms of a trig function. Well, let's rewrite that as 1 over cosine of x. This is the same thing as this quantity squared, right? And I know 1 over cosine of x is secant of x. So I can rewrite 1 over cosine of x to be secant of x. So this is secant x quantity squared, which normally we write as secant squared x. So we just derived the derivative. We have the derivative of tangent of x. This is equal to positive secant squared x. So all of the other trigonometric functions, again, can be derived by using the quotient rule. If we look at our other trigonometric functions, cotangent of X can be rewritten in terms of sine and cosine. Yeah, cotangent. That's the same thing as cosine of X over sine X. If we looked at secant X, this is the same thing as 1 over cosine of X. And if we look at cosecant of X, this is equal to 1 over sine of X. So we can derive these derivatives using the quotient rule. Pause there. So I want to just show you maybe one more of them. We might do them all, I don't know. So let's look at secant of X. So if I have the derivative of secant of X, I would first want to rewrite this in terms of sine and cosine, but secant is 1 over cosine of X. So this is d dx of 1 over cosine of X. Well, if I do the quotient rule, the derivative of 1, I'm not going to write down that I'm taking the derivative of the numerator and all those steps. I'm just going to do it. So the derivative of the numerator is 0 times the denominator cosine of X minus 1 times the derivative cosine of X, which is negative sine X, all over the denominator squared, cosine squared X. Well, I have negative times a negative, so that's positive. So this is equal to sine of X all over, I'm going to rewrite cosine of squared of X as cosine X times cosine X. So the trick here is that we're going to break this up as 2 fractions multiplied together. So we're going to write this as sine X cosine over cosine of X times 1 over cosine of X. And so go through and rewrite what trigonometric functions those are. Well, sine over cosine, that's tangent X, and 1 over cosine is secant X. So the derivative of secant is tan secant. Tangent X times secant X. So same sort of idea. The cosecant is going to be faster because our numerator is just a constant. Derivative of the constant is going to give us 0. So let's just do that really quick. So d dx, and then it's good to kind of see it, and then you can kind of think of ways to memorize how to remember them. So the derivative of cosecant X, well, that's still the same thing as the derivative of 1 over sine X. Well, if we take the derivative of the numerator, that's 0. So times the denominator is 0. So minus 1 times the derivative of sine X, which is cosine of X, all over the denominator squared. So that's sine X times sine X, or sine X quantity squared. But we're going to leave it as sine X times sine X. Same sort of idea that we did over here. We're going to break it up as 2 separate fractions and multiplying those 2 separate fractions, negative cosine X over sine X, all times 1 over sine X. Well, cosine over sine, that's cotangent. So this is negative cotangent X. And 1 over sine X, that is cosecant X. So the derivative of cosecant X is negative cotangent of X times cosecant of X. The other one is the one that's going to take a little bit longer because the numerator cotangent, yeah, I'm doing this pretty fast, cotangent of x. So derivative of cotangent of x, this is the derivative, rewrite it in terms of cosine and sine of cosine of x over sine x. Well, taken using the quotient rule, the derivative of cosine, that was negative sine x, times the denominator sine x, minus the numerator cosine of x, times the derivative of sine x, which is cosine of x, all over the denominator squared. So it is actually sine squared x. Well, sine times sine, and let's notice they both have a negative. So let's just pull a negative out while we're rewriting this. So pulling out a -1, we have sine squared x plus cosine squared x all over sine squared x. Well, sine squared x plus cosine squared x, that is the trig identity of 1. So we have -1 all over sine squared x. Another way to write this is -1 all over sine x. The 1 over sine x we can think of as squared. I just left the negative out front because if I squared the negative, that would make it positive, and I don't want to do that. And I know 1 over sine x is cosecant x. We have negative cosecant squared x. So the derivative of cotangent is negative cosecant squared. So you should be able to derive those pretty quickly if you didn't remember them, so that you could use it. Okay, so right in front of you are your derivatives of your trigonometric functions, and I'm trying to explain maybe how you can kind of remember this. So we talked about how we can remember which one was positive and which one was negative when we were taking the derivative of sine and cosine. If we're looking at the derivative of cosine of x, it had to deal when we're looking at the graph of it, it was decreasing at first. It started at 1 and it was coming down. And that's where this negative comes in. Where the derivative of sine x, it's increasing at first. That's positive slope. And that's why we had a positive here. So the other ones, tangent and cotangent, those are both the squares. Maybe think of it, they both have two trig functions if we rewrote them, and that's where we're getting the square from. If you see that tangent and secant x, well, this is secant squared of x. And so secant of x is the trig function that uses it, tangent of x, and itself. Where if I look at cotangent squared of x, notice that the trig function it uses is cosecant of x. And in here, we have cotangent and we have cosecant itself and the one that uses it twice. So if you can kind of remember it that way, and then to kind of remember which one's positive and which one's negative, I saw this helpful hint is the ones that if when you say the trig function has the co in front of it, it's negative when you take the derivative. So cosine, the derivative of this is the negative. Cosecant, so the derivative of cosecant, that function is negative. And the derivative of cotangent, it has the co in front, that one is also negative. Any of the other ones were positive. Sine, when you say it doesn't say co something, Tangent, no co, and secant, no co. Notice those were all positive. So maybe, hopefully, those are kind of ways that you can remember or help you remember which trig function is which. But those are the things that you want to be able to hopefully recall pretty fast while you're doing these problems. And so pulling up an example using the differentiation rules that we were just learning in this class and the derivative of trig functions, we should be able to find the derivative of y equals x squared cotangent of x minus 1 over x squared. Looking at this, you should be able to examine and look at what types of rules that you need to use. And so if I look at this and I don't manipulate it anyway, then I would have to use in here the product rule. Because of this minus in here, we're using the difference rule. And then if I don't rewrite 1 over x squared, which we talked about that we could rewrite that, if I don't rewrite that, then I'm going to have to use the quotient rule. So I think the general power rule, if I can use that, is a lot faster to me than the quotient rule. So I might start by rewriting this a little bit. So we have y is equal to x squared times cotangent of x minus, so let's rewrite 1 over x squared using the rules of exponents. We can bring that x squared up into the numerator, changing the sign of the exponent. So this is minus x to the negative 2. So now I can just use the product rule, my difference rule, and in the last case, it's no longer the quotient rule. This is the general power rule. So dy dx, we're looking at the derivative of the first. So d dx of x squared, all times the second, cotangent of x, plus the first, x squared, times the derivative of the second, so derivative of cotangent of x, minus, using the general power rule, I think I can probably do that right here. So let's bring down the power in front, negative 2, x, and then let's subtract 1 from the exponent. So negative 2 minus 1 gives us a negative 3 exponent. Well, derivative of x squared is not bad at all. That one gives us 2x. Derivative of cotangent, it has a co in it. Let's put the negative there. Cotangent, that one is cosecant. And cotangent is going to have itself in it. So it's going to be cotangent x, cosecant x. Plus x squared. What did I just do? I just made a mistake, didn't I? I should have taken the derivative of cotangent x over here. So let's go back. And this right here should have been, I should have left cotangent of x by itself. Plus x squared. Now let's restate that. So the derivative of cotangent of x is itself, cotangent x. It has a cot in it, so we said it was negative, times, this one was cosecant x. And then we have a minus, so that's really a plus 2. We might as well rewrite x at a negative 3 as bringing that down to the denominator, making the exponent positive. So plus 2 over x cubed. So looking at this, we have 2x cotangent of x minus, let's pull that negative out front, negative x squared cotangent x cosecant x plus 2 over x cubed. So just putting all together the rules that we've been learning. Okay, so I made an error and I'm glad I didn't, and maybe hopefully you caught that while you were going through the video, and I just went through it, that the derivative cotangent of x, that one was the cosecant squared. And so right here, this derivative, when we took this, was cosecant squared. So this is negative cosecant squared x. So right here, we pulled the negative out, but this should be in here, cosecant squared x. So another example, and we're just pretty much tying in again what we've been learning in this class. And we've looked at tangent lines, we've looked at finding the equation of tangent lines. And so this example says graph the curve of y equals sine x over the interval negative 3 pi halves, which is less than or equal to x, which is less than or equal to 2 pi. And we're also going to want to graph that tangent line. So find the equation of the tangent line at x equals negative pi, 0, and 3 pi halves. We're running low on time, so I'm just going to do as much as I can, but let's first graph it. And so let me just go in and put my intervals, and it helps me. And this is sine of x. There's no phase shifts. There's no stretching. So I'm good. So let me just go in here and do my intervals of my quadrantal angles. So pi halves, pi, 3 pi halves, 2 pi. So if I went in the other direction, this would be negative pi halves, negative pi, negative 3 pi halves. So I think to myself, well, sine of 0 is 0. So I'm starting this one at the origin. I am not reflecting this any place because I don't have any negative. So I would go up and I would hit 1. I would come back and turn around and I would hit pi at the origin. Continue past the x-axis, hit negative 1 at 3 pi halves, and at 2 pi, I'm back up at the x-axis. At negative pi halves, I would be down at negative 1. At negative pi, I'm back up at the x-axis. And at negative 3 pi halves, something's wrong, is something wrong there? Negative 3 pi halves, no, it's positive 1. Okay, so we graphed the sine function like it wanted us to, and it wants us to find the equation of the tangent line. Well, we know we need to find the slope or the derivative. We need to be able to find the slope anywhere on sine of x, so we need to find the derivative of sine x. So dy dx is equal to, well, derivative of sine is cosine x. And so now let's look at the derivative when x is negative pi halves. So let's do this when x is negative pi halves. So if we go in here and we plug in negative pi halves, wherever we see an x in our derivative function, we have the following. So a couple ways we can approach evaluating this. We could think of cosine as an even function. So cosine of negative x is the same thing as cosine of x. You can think of it as looking at your unit circle. Negative pi halves tells me I'm going clockwise. So if I think about on my unit circle, cosine is my x value. What is x when I get to negative pi halves? Oops, and I should have said just negative pi. Oops, so let's go back over here. So negative pi would get me here. So again, cosine is your x value. So your x value at negative pi halves is -1. So my slope, when x is negative pi, is -1. Our point, negative pi, -1. So we have these two values. We can figure out what b is. So point right here. Our slope is -1. And we can find b. So plugging in our point, so we have y, which is -1, equals m, which is -1 times x, which is negative pi, plus b. So I have -1 equals pi plus b. So solve for b. B is equal to -1 minus pi. So my equation of this tangent line is y equals my slope, -1 times x plus b. So just put in this expression, -1 minus pi. So we could do the same exact thing when x is 0 and when x is 3 pi halves. If you do this, and I just don't have time, but if you do this, you'll find that your slope in here is 1. And at 3 pi halves, you should find, look at this, this is where it changes direction. We should find that our slope is 0.